Okay, so we're going to look through a set of past paper questions now on relative frequency. Relative frequency questions could appear on the higher tier or the intermediate, and potentially on the calculator or the non-calculator, depending on how complicated the numbers are. And basically relative frequency is probability, experimental probability, where by increasing the number of times you repeat an experiment, the more reliable the outcomes become. So let's take a look at how these look. So usually there's a lot of information with a relative frequency question in order to give you the context. So it's important that you read the question carefully. So here we've got an experiment that was carried out to investigate the probability of obtaining a head when a biased coin is thrown. So if it's biased, it means that you no longer have that equal chance, or a head or a tail being equally likely. Sort out the focus. It's a bit better. The number of times the coin landed and showed a head in 4 sets of 10 throws is shown in the table below. So in this column, in this row here, out of the 10 times the coin was thrown, head was recorded twice, so the other 8 times it was a tail. Then in the next 10 it was 4, and so on and so forth. Complete the table below to show the relative frequency of obtaining a head after throwing the coin a total of 10 times, 20 times, 30 times, 40 times. So what we're doing is like a cumulative frequency. Rather than deal with each set of 10 on their own merit, once we get to there, we've actually thrown the coin 20 times, and out of those 20 times there were 6 heads. When we get down to this row, we've thrown the coin 30 times, and that is how we build up this relative frequency table. So usually they'll start it for you, which is always a good clue. So you can see here that this relates to this table. After it was thrown 10 times, 2 out of the 10 were heads, and 2 out of 10 as a decimal is 0.2. After it's been thrown 20 times, we're at this point, so out of the 20, 6 were heads. 6 out of 20 is 0.3. So for us to continue this, after it's been thrown 30 times, the number of heads is 7, 8, 9 out of 30, and then to turn that into a decimal, we do 9 divided by 30 and hit your SD 0.3, and then out of 40 it's the total of all of those, which is going to be 10 out of 40, which is 0.25. Using the above results, write down the best estimate for the probability of obtaining a head when this biased coin is thrown. Now, with any experiment, the more times it's repeated, the more reliable the outcome becomes. So the best estimate out of that table is 0.25, and that's because that's the relative frequency after the most repeats of the experiment. So it's the most reliable because it's measured after the most throws. So 0.25, it's the most reliable because it's measured after or from the most throws. So the way that that scheme is marked is there would be 1 mark for completing the 2 fractions. There would be 1 mark for correctly turning them into decimals. There would be 1 mark for the 0.25 and an explanation mark for saying that that's the most reliable because it's after the most repeats of the experiment. Okay, let's take a look at the next one. An experiment was carried out to investigate the probability of obtaining an even number when a biased dice is thrown. The number of even numbers obtained in each 5 sets of 20 throws is shown in the table below. So the first 20, there were 14 evens. The second 20, there were 8. So in the first 40, there were 22, and so on. Complete the table below to show the relative frequency of an even number occurring after throwing the dice a total of 20, 40, 60, 80 and 100 times. So we'll do the fraction first of all. So after 40, that's those two, 22. After 60, we've got those 22 and another 14, 36. Then after the next 20, we've got 36, and now we've got another 16, so that's 36, 46, 52 out of 80, and then after 100, it'll be 62. So all we're doing is accumulating up the number of heads after each set of 20. To turn those into decimals, 14 out of 20, 0.7, 22 out of 40, 0.55, 36 out of 60, 0.6, 52 out of 80, 0.65, and 62 out of 100, 0.62. Using the above results, write down the best estimate for the probability of obtaining an even number when this biased dice is thrown. Give a reason for your answer. So best estimate is the most reliable after the most throws, so it's 0.62. Y is the most reliable after most throws. Part C. Explain what you might think happened to the relative frequency if the experiment was continued with more throws of the biased dice. So what they're looking for there is for you to say that this will settle, it'll stabilize. So it started off at 0.7, then came down to 0.5, 0.6, 0.5, 0.65, 0.62. It looks like it's settling around the 0.6, 0.61, 0.62. So you would say the relative frequency will stabilize, or it'll settle down, smooth out. That type of language is what they're looking for you to use. What would be your best estimate of the probability of obtaining an odd number? Okay, well, if our best estimate of obtaining an even one is 0.62, you need to know that total probability adds up to 1. So you'll be doing 1 minus 0.62, which is 0.38. Okay, so the way that the marks are awarded for that one is there's 3 marks for correctly completing the table. You get 2 for 6, 7 or 8. So that's all. B2, 6, 7, 8 correct. And 1 for 4 or 5 correct. For this one, you'd have 1 mark for the 0.62 and an explanation mark for why it is that. You get another explanation mark for saying that you would expect it to settle down or stabilize. and here there'd be 1 mark for the method of taking your probability away from 1, and 1 mark for the answer. Question 3. Yasmin carried out an experiment. In the experiment, she shot 10 balls at a target and recorded the number of shots hitting the target. She carried out this experiment 6 times. The results are shown in the following table. So in this group here, out of the 10 throws, she hit the target 3 times. In this group here, out of 10 throws, she hit the target 5 times. So in 20 throws, she hit the target 8 times. That's where the relative frequency builds up from. Yasmin decided to draw a graph showing the relative frequency of shots hitting the target after 10, 20, 30, etc. Use the graph paper opposite to draw the graph of the relative frequencies. So there's the graph paper, but before I can use it, I have to calculate what those relative frequencies are. Now in the first 2 questions, they set that table up for us. So this is more difficult because you've got to know what you're doing. So I don't want first, second, third, fourth, fifth. I want total shots. And that would be 10, 20, 30, 40, 50, 60. Then I want total hits, because that's what we're measuring. So in the first 10, there were 3. In the first 20, there were 8. In the first 30, there were 8 and 4, 12. In the first 40, there was 16. In the first 50, there were 18. And in the 60, there were 20. So I'm just adding up those as I'm going. Then to turn that into a relative frequency, here it's going to be 3 out of 10. Here it's going to be 8 out of 20, 12 out of 30, 16 out of 40, 18 out of 50, and 20 out of 60. So those are the relative frequency as fractions, but I need them as decimals in order to plot them. So that one I know is 0.3. 8 divided by 20 is 2/5, which is 0.4. Then I've got 12 out of 30, which is 0.4. 16 out of 40, 0.4. 18 out of 50, 0.36. 20 out of 60, 0.33. That's 3 recurring, so it's 2 decimal places, 0.33. Okay, so now I know what I'm plotting. I'm plotting 10, 20, 30, 40, 50, 60 against the decimal relative frequencies. So 10.3, 20.4, 30.4, 40.4, 50.36, 60.33. So you can see here what we were talking about earlier about it starting to settle down. It's starting to come around about the 0.3 to 0.35, you would guess. Okay, B. Do you consider that the experiment has been carried out enough times to give a good estimate for the probability of a shot hitting the target? Now, interestingly, you could answer yes or no here and get this mark, provided you back that up with a reasonable argument. So if we wanted to argue yes, we'd be arguing yes because all of the shots are between 0.3 and 0.4. So it looks like it's going to settle down between 0.3 and 0.4. Appears to be stabilizing between 0.3 and 0.4. So that would get you the mark. But you could argue, no, because of this run up here of 0.4, 0.4, 0.4, there's not enough to see what's going to happen. Is it going to start rising again to stabilize there, or fall to stabilize there? So you could argue no, that it doesn't appear stable yet. So bizarrely, yes or no would be good enough, so long as you put a reasonable argument why. So marks for that, there would be 1 mark for the running total 3, 8, 12 and so on. There would be 1 mark for writing it as fractions, and then 2 marks for turning them into decimals, and 1 mark for plotting correctly. And then your explanation, as I said, could be yes or no. What's important is the case you make for why it's yes or no. And go back to that table. Generally, we wouldn't join those points up, but you wouldn't be penalised if you were to join them up. But you would be penalised if you put bars on them. Question 4. Alan is a professional darts player. He claims that with every throw, he can hit the bullseye with a probability of 50%. Fionn challenges him to prove this by throwing 5 sets of 10 darts. Alan's results are given in the following table. So in the first 10 he hits 4 times, in the next 10 8 times, so in the first 20 12 times. So we can see how the table is building. So let's complete the table. In the first 30 it'll be 12 15, so that will be 15 out of 30, which is 0.5. In the first 40 it'll be 18, which will be 18 out of 40, and in the first 50 it'll be 20, which will be 20 out of 50. 18 out of 40, 0.45, and that's 0.4. So that's the table complete. Then we have to draw the graph of the relative frequencies. So 10, 0.4, 20, 0.6, 30, 0.5, 40, 0.45, 50, 0.4. Is Alan correct to claim that he has a probability of 50% hitting the bullseye? Well, the best probability that we've got is the one after the most throws, which is 0.4. And the more throws that have happened, the more it's tending towards low 0.4s rather than 0.5, which would be 50%. So I would say no, because the probabilities, the relative frequency, suggests low 40%, success rather than 50%. So something like that you want to be arguing. So no, the relative frequency is lower, the probability is lower, it's stabilizing below 0.5, something like that. Okay, so the marks for that, there'd be 1 mark for the completion of each row. Then you'd have 2 marks for correctly plotting and 1 mark for the correct argument. Question 5. So the next two are trickier. A potato producer uses a machine to sort his potatoes. The potato producer carried out a survey to investigate the probability of oversized potatoes passing through his sorting machine. The relative frequency of oversized potatoes passing through the machine was calculated after a total of 100, 200, 300, 400 and so on potatoes. The results are plotted on the graph below. Write down the best estimate for the probability that one of these potatoes selected at random will be oversized. So as we've done with the previous questions, the best probability is the one after the most trials. So at 600 you've got 0.424. 0.44 is the best estimate, and we're saying most reliable after most trials. Okay, so in your words, that's what you're arguing. The more times that it's been measured, the more reliable the measure. Okay, so now we've got to use this. The trader offers to buy oversized potatoes at 15 pence each. How much would the potato producer receive if he decided to sell to the trader all the oversized potatoes in the first 100 sorted by the machine? So in the first 100 it means this hasn't happened yet. So our probability is 0.4. So the relative frequency is 0.4. So the number we'd expect to have that are oversized is 0.4 of those 100. So you have 40 oversized potatoes. And he's going to sell each of those at 15 pence each. So if we times that by 0.15 to have it in pounds, he'd be making £6. The potato producer decides not to sell his potatoes to the trader. He sells 900 potatoes to a market stall holder. The potato producer sells his potatoes at £4.50 for 100 potatoes. He's agreed with the market stall holder that he will give a 2 pence refund per oversized potato discovered. What would your best estimate be for the amount he would expect the potato producer to make from this transaction? Well, let's deal with it in two stages. He's going to sell all his potatoes at £4.50 per 100. So he's going to have 9 lots of £4.50. £40.50. You can't see that, can you? £40.50. So if they were all of the proper size, that's what he would be getting off the trader. But some of those are going to be oversize, and our best estimate is 0.44 lots of those 900. So our estimate for the oversize will be 0.44 times 900, 396 oversized, and he's going to pay back 2 pence for every one of those. So the refund will be 396 lots of 2 pence, so in pounds, £7.92. So the amount he's going to make is the difference between what he would have got and the refund. £40.50 less the refund, £32.58. Okie doke. So the mark scheme for that is 1 mark for the site to 0.44 and an exclamation mark for the reliability. Then for part B, 1 mark for the 0.4, then 1 mark for the getting the 40 and the 0.15 and correctly multiplying them to get the £6. And for part C, one mark for using the 0.44, one mark for correctly multiplying by 900 and 2p, getting the £7.92, one mark for the £40.50, and one mark for 4, a method mark for the £40.50 and its answer, and then a final mark for working out the difference. So 2 marks for getting the £40.50, 1 mark for correctly using our best probability, 2 marks for getting the £7.92, 1 mark for working out the difference. One more to look at, which is again relative frequency, but without actually drawing any graphs. So a factory production line packs buttons into bags. There are exactly 80 buttons packed into each bag. There's a mixture of different coloured buttons in each bag, and 600 bags were packed in a day. The first 100 bags were checked, and it was found that a total of 1,200 red buttons had been used. In the 600 bags of buttons, it was found that the relative frequency of red buttons packed was 40%. Calculate the relative frequency of the red buttons packed in the final 500 bags. So they're giving us the relative frequency here, and that's what we need to start with. So the total number of buttons packed that day is going to be 80 times 600. So 80 lots of 600 is 48,000 buttons. Now, we can use the relative frequency to work out how many of those were read. Would be 40% of 48,000. So if I multiply that by 40%, I get 19,200. If you didn't want to use your percent button, write that as 0.40 times that, it will give you the same thing. So 19,200 read. Now if there were 19,200 read ones altogether, and there were 1,200 read in the first 100, then in the final 500 it would be, that's how many in total, that's how many in the first 100, so 18,000 red buttons in the final 500. The number of buttons in the final 500 would be 500 lots of 80. $40,000. So the relative frequency of the red buttons, there are 18,000 out of the 40,000. The pen's running out. So the relative frequency of reds in the final 500 would be 18,000 out of 40,000. Which is 9 out of 20, or 0.45. So the relative frequency of the red in the final 500 is 0.45, or 45%. So that's quite a weird one. It's much less like the previous questions. So 7 marks for that question. 3 of them were for getting that 19,200. So doing the 80 times 40% times that. Then there was 1 mark for working out how many reds that left. And then 2 marks again for doing the working out the 40,000 and writing that as a fraction and getting your final answer. So 2, 3, 4, 5, 6, 7 marks. So that one was probably the most challenging of the relative frequency questions that came up, and in fact you could work through that just by dealing with the percentages rather than worrying about the fact it's a relative frequency.